Yeah, please.
So today I'm going to talk about a variational approach. To generalized Ricci solitons. Generalized Ricci solitons. So the plan is first to get some intuition from the Keller setting, and then maybe see what we can say in generalized Keller setting. And actually, we will have quite specific generalized Keller setting, which is we call log non-degenerate. So specifically, the Poisson Tensor associated with the structure will be generically invertible. And it's very interesting whether what I'm going to tell is extendable beyond this. So I sort of expect that it is, but I don't have an answer. So let's start with the Keller setting. If you have a Keller manifold M, complex structure I, and Keller form omega, then you have a very easy procedure to deform your Keller form by adding to your given omega DDC of a function. And as long as this is positive, as long as omega phi is positive definite, this defines another Keller structure. Another Keller structure. So here phi is a smooth function on your manifold. Smooth real valued function. So basically, you can identify a certain set of Keller forms with an open subset in the set of all smooth functions. And specifically on a compact manifold, so if M is compact, then the set of classes which you can produce this way coincides with a set of classes which represent the same class in cohomology. The set of Keller forms which represent the same class in cohomology as the original one. So this is due to DDC lemma. So it gives you a very good understanding of what a given, how you can deform, and actually gives you a good explanation of what the set of this deformed classes is. It's essentially the set of all Keller forms in the same cohomology class. So this is identity in the second cohomology. And the driving set of questions in Keller geometry is the search of canonical metrics in such set. So such set, maybe I'll write a name. So it's called Keller class. And the principal questions in Keller geometry all revolve around search of canonical metrics in various Keller classes. Search of canonical metrics. In a given Keller class. So examples of such questions are first the Yau solution to Calabi problem, specifically what he proved, that you can, if C1 is 0, then in a given Keller class, we can realize any volume form, any Ricci form. And another problem which is much more complicated and sort of was partially settled recently is the search of constant scalar curvature Kähler matrix. So you, in a given Kähler class, you're trying to find metric with a constant scalar curvature in the usual Riemannian sense. And of course, if your manifold is Fano, if M is Fano, that is your first Chern class is positive, then you can look for omega in this first Chern class such that the Ricci form of omega is proportional to omega. And this is Kähler-Einstein matrix. So there are many other types of metrics which people are interested in. There are Kähler-Ricci solitons, shrinking Kähler-Ricci solitons related to Kähler-Einstein matrix. There are complete steady Kähler-Ricci solitons, basically generalizing the Calabi-Yau's matrix. And in all these cases, what we do, we essentially look for canonical metrics in a given Kähler class. So the way these problems are often approached and maybe conceptualized, and in general, it's a very powerful tool in Kähler geometry. These problems are studied through functionals. So we can take a Kähler class. I didn't give it any name, I think, actually. Yeah, maybe I'll call it H sub omega. So it's a Kähler class defined, or maybe H is a bad name. M sub omega. Script M sub omega. So the way it's done, so we can often define a functionals on this Kähler class. And there is a whole zoo of such functionals. And the entire idea is that in many geometric settings, these are convex. And existence of canonical metrics, is controlled by properness features of this function, by properness of these functions. So properness is sort of vague. So there are many ways you can define properness, and you will get different type of results. But that's an overall philosophy here. So it will be good to try to extend some of these ideas to the generalized Kähler world. And to do this, we need to basically overcome two problems. First, we need to find an appropriate definition of generalized Kähler class. Then once such definition is found, we need to take appropriate notion of canonical metric. And again, there are many choices. And for some of them, we might expect to find some nice functionals and maybe study those functionals in order to understand the existence of canonical metrics. So that's what I'm going to talk about, and we're going to consider very kind of narrow and specific geometric setting. So it's basically should more serve like an evidence of the fact that the whole methodology works in generalized Kähler world, and maybe it can be extended beyond to other types of metrics as well. So that's the idea. So now let me get specifically to generalized Kähler structures, and I will use throughout this talk by Hermitian point of view on generalized Kähler structures. So because it's sort of a little more down to earth, it allows us to explicitly write down all our functionals and explicitly study them. But certainly it will be nice to extend everything what I'm going to talk to through the language of generalized geometry. It will be certainly beneficial because probably it will answer the question how we can generalize it to a little more wide setting than the one I'm going to talk about. So let me recall the definition. So what we started with is a quadruple. We have a smooth even dimensional manifold with a Riemannian metric and two complex structures. So I and J are integrable and G orthogonal. So metric is compatible with both of them. Integrable complex structures. So from these two, you can form 1-1 forms. So omega I is the one if you plug in I in your metric, and omega J is the one if you plug in J in your metric. So these are fundamental 1-1 forms. One arm is a holomorphic type with respect to I or J. And they satisfy the following assumptions. First, they both are, so, okay, let me write down. So if I calculate dci of omega I, it will be the same as negative dcj of omega j. And I call this H. So H is essentially 3-form on your manifold. So where I recall dci or dcj is a twisted differential where you twist the usual de Rham differential with the action of your complex structure on a differential form. So you act component-wise. And this form H is closed, so dH is 0. All right, so that's a setting which we'll be working with. And maybe let me give a couple consequences of this formulation. So once you have this this data, you can always cook up to symplectic forms. So you know them F plus and F minus. So F plus is minus twice G I plus J inverse, and F minus is the same thing where you take the difference of complex structures. So these are symplectic whenever they define. They're not necessarily globally defined because you have to take inverse of an operator which might not be invertible. But if they define, they are symplectic. And it's just a formal consequence of these assumptions on the generalized scalar structure. And another piece of data which we will need is a Poisson tensor, which I define like this, G inverse. So again, it's a consequence of generalized scalar structure of this defining equations that this is necessarily Poisson tensor, which means that if you take the extension of Lie bracket of this thing with itself, you'll get 0. And sigma is an element in the exterior power of the tension bundle. Is a section. So actually, whenever F plus or F minus is well defined, you can recover a metric explicitly from your complex structures. So you have a bunch of identities. For instance, your metric G can be obtained as symmetric part of F plus J, or symmetric part of F minus J. So F plus is not compatible, not necessarily compatible with J. So this two tensor is not necessarily symmetric, but if you take its symmetric part, it will be exactly your metric tensor. So maybe let me draw a picture which sort of informs of what's going on with this F plus and minus and sigma here. So what do you happen to have? So if this is your manifold M, that what you happen to have two subsets. One subset where I plus J degenerates, and another subset where I minus J degenerates. And of course, in principle, they could be entire manifold. It's not forbidden. So maybe I'll call this the Z plus and Z minus. However, what you can always show that these are sort of rigid. What you can demonstrate that the union of Z plus and Z minus is simultaneously I and J analytic. So it's analytic subvariety of M with complex structure I, and it's analytic subvariety of M with complex structure J. And the reason for this is that this is actually the zero set of sigma plus square root, minus square root of minus 1 I sigma, which happens to be holomorphic, I holomorphic Poisson tensor. So, and being holomorphic section over holomorphic bundle, its zero set is an analytic subset. So it shows that it will be analytic with respect to I, and analogous argument shows that it is analytic with respect to J. But of course, it can Z plus union Z minus could coincide with the entire manifold. And our assumption through the most of today's talk is that actually this is a proper subset. Again, it's not necessarily true, it's quite restrictive, but we mostly will assume that Z plus and Z minus union Z minus is a proper subset. We mostly assume that Z plus union Z minus inside of M is a proper subset. So it's not entire M, and it means that at least it at least has a real codimension too, because it's an analytic subset. Okay, so maybe I'll make a little remark about dimension 4. So this is a special case when dimension of your manifold is 4, then actually Z plus turns out to be the set where I equals negative J. Maybe I rather should write it as I plus J equals 0. And Z minus is a set where I minus J equals 0. And thus, so it's just a purely for dimensional reasons. You basically can write down the this set. And for this reason, because these clearly do not intersect each other, so you have actually that these are disjoint. And it is important if you want to study the existence of generalized scalar structures on complex surfaces when real dimension is 4, precisely because this gives you two disjoint analytic curves in your surface, and this is sort of rare if you think about non-Kähler surfaces. Not rare maybe, but special in any case, not generic. So maybe let me give a couple examples of the structures, so just to show that these structures exist, which we're talking about. So if you start, if you take as your manifold C2 minus the origin, and you quotient it by contraction, and I'll choose the simplest contraction when you identify points to Z and the point Z. So this is so-called standard Hopf surface. So on this Hopf surface, it's naturally a complex manifold. It has a complex structure which it inherits from C, and it also has a metric, special metric, this specific Hopf surface, which I will call cylindrical. Basically, if your coordinates Z1 and Z2 in a complex space, then this metric is dz1 bar plus dz2 bar divided by norm z1 squared plus z2 squared. Well, technically, since G is a Riemannian metric, I need to take real part of that. Okay. So that's metric compatible with complex structure, the one you have inherited from here, and such that ddci of omega I is 0. So what do we have? I'm G and one complex structure, and ddci of omega I is 0 for this specific metric. So to turn it into a generalized scalar structure, you would like to find a second complex structure. And it turns out that you can do that, and actually in several different ways. The one which will be relevant to us is a complex structure, which you can get from the first one by pulling back with respect to an involution. So there is an involution here. Involution. Which is given by composition of reflection in, say, plane Z1 equals 0, and reflection, or rather I should say inversion in the union sphere S3 inside C2 minus origin. Oh, so the plane actually, the real part of Z1 equals 0. So this map from this space to itself, it actually preserves orientation because it's a composition of two reflections. And so J and I then use the same orientation, and you can check that the Poisson Tensor here actually is non-degenerate, and it is given by the constant multiple, which I'm not sure about with this convention. So real part of Z1, Z2, del Z1, wedge del Z2. So it's generically invertible, but it vanishes on the two loci. One is when Z1 is 0, and the other when Z2 is 0. And even though they intersect, of course, in C2, they do not intersect on M because we removed the origin. So that's a prototypical example of a manifold we should think about in terms of what we're going to discuss. Any questions?
Does this correspond to conjugating the second coordinate or the first coordinate, or is it different?
It's like conjugating with respect to second coordinate. Yeah.
Okay.
And there is a choice. You can conjugate with either of them. Basically, it's changing one of the complex structures to negative that. All right, so now I want to discuss generalized scalar class. And to this end, I will need to present Hamiltonian flow construction. So it really appeared in generalized scalar geometry many times in different papers. So it was attributed to Joyce in the paper of Apostle of Godishon and Grancherov. It then appeared in Hitchin's work. Then it was in Marcos' works. Then this generalized scalar class formulation, which I'm about to present, appeared in the Jeffs and Matt Gibbons Gibson paper. So let me describe it. So again, we start as before with generalized scalar manifold. Is GK manifold, and at this point I actually don't have to make any assumptions about being logged on degenerate or anything, so it can be any generalized scalar manifold. So with sigma, the associated Poisson tensor, which I recall given by commutator of INJ G inverse. So this is Poisson. So whenever you have a Poisson tensor and a smooth function, you can always cook up a Hamiltonian vector field, which I will denote x sub phi. So by definition, we set it as negative sigma applied to d phi. So phi here is a smooth function on your manifold. So it's a consequence of Poisson condition that this vector preserves Poisson tensor. And actually, the set of Poisson Hamiltonian vector fields. So you can consider all Hamiltonian vector fields, which I will call H of sigma, H sub sigma. So H sub sigma together with the usual Lie bracket is a Lie algebra. And so this is Lie algebra. So commutator of Hamiltonian vector fields is again a Hamiltonian vector field. And specifically, this vector algebra is isomorphic to the space of smooth functions modulo constants, well, because constants generate trivial vector fields, with a bracket given by negative sigma. Maybe I should write a little bit more explicitly. Negative d phi 1, d phi 2. Sorry. Negative sigma applied to d phi 1, d phi 2. So this is just Lie algebra of Hamiltonian vector fields with respect to Poisson tensor. So we all know it well in the case of symplectic structure, but it works equally well if you don't have a symplectic structure, but you merely have a Poisson structure. So now let me make a key definition. This is Hamiltonian flow construction. Hamiltonian flow, I call it deformation. So we take phi sub t, a one parameter family of smooth functions on your manifolds, on your manifold M. And really everything depends on these functions up to a constant. So really it's a member of the space. And then we can consider the same manifold with GT, JT, and IT. So these will be one parameter families of metric and complex structures. And these one parameter families are defined by their variations as follows. So J is actually stationary, so J doesn't change. I does change, but it changes in a simple way. It's just pulled back by the vector field X sub phi t. And the metric changes in the most complicated way. So the derivative of the metric is ddci phi t. So it's antisymmetric tensor. Then we compose it with J. It becomes of mixed type, and we take its symmetric part. So then this manifold with this one parameter family defined by this deformation, so is also generalized scalar as long as GT is positive definite. Okay. So let's look a little bit at this definition. So what it allows us to do, essentially, it gives us a local action of a group with this Lie algebra or with this Lie algebra. So an action of a group with this Lie algebra on the space of generalized scalar structures on a given manifold. It's local exactly because of this condition. So we cannot act by any element of the group because any action might make your metric being not positive definite. But locally, if we act by element in the neighborhood of identity of the corresponding Lie group, you will get a new generalized scalar structure. So let me write this down. So it's a local action of an infinite dimensional Lie group, which I call H sigma, with Lie algebra, which we defined before, Lie algebra of Hamiltonian vector fields H sigma on the space of generalized scalar structures on M. All right, and what we can do, we can define generalized scalar class is an orbit of this action. So you start with a one generalized scalar structure and you act by this one parameter Hamiltonian deformations in all possible way. And the set of generalized scalar structures which you obtain will be called generalized scalar class. It's a little bit implicit and it's not as nice as in the Keller case, specifically because of the fact that this phi t is one parameter family which might change along the deformation. So this is unavoidable. We have to consider those. So generalized scalar class, I will usually call it just by script M. But as a sanity check, let's verify what it tells us if we start with a Keller structure in the beginning. So if the initial structure is Keller, structure M G I J is Keller. Well, if it is Keller, what we actually have, that Poisson tensor vanishes, because Keller, by what I mean by that I equals J and the triple MGI is Keller. So since I equals J, your Poisson tensor is really 0 here. And since Poisson tensor is 0, it implies that the vector fields which we consider the Poisson vector fields are identically 0. So if we go back, if we scroll to the definition of the deformation, it tells us that the second complex structure also doesn't float. So J stay fixed and I also stay fixed. And I equals J, and if we look at the way the metric changes, so remember I equals J. So this will be a symmetric tensor, and this evolution equation, maybe I'll just copy it. So this evolution equation will be rewritten in the Keller case as the variation of 1-1 form being given by DCI phi. And this is exactly deformation within a Keller class, a usual Keller class. So, and you can explicitly integrate this deformation. So if you actually have a one parameter family of such functions and you apply this one parameter family of diffeomorphisms, then what you get at some time t is actually your initial metric at time 0 plus ddci of integral from 0 to t phi t dt. So again, this is exactly the way we describe it. You take your initial metric and you add ddci of a smooth function. So at least it makes sense in Keller case. Maybe I'll make a little remark. that you can actually consider case when MGI is maybe non-scalar, yet sigma is 0, and these are known as commuting case. So if you're in a commuting case, we still have I and j fixed, and the advantage of this special case that it actually gives you linear structure on a generalized scalar class. Maybe I shall call it a fine structure. So it's like you have this additive structure like you have in the Keller case, which is actually lacking in general, and this causes some practical problems in applying this construction. Any questions? All right, so that was about Hamiltonian deformations of a generalized scalar structure. Now let me talk about specific, and we define generalized scalar class. Now let me call about canonical distinguished matrix, which we'll be looking for in the given class. And this will be generalized scalar solitons. Again, perhaps this is not the only relevant type of metric structures in this setting, but yeah, this is the one we're considering. So let me recall you this definition which we have seen in our last session last year. So if you have a generalized scalar structure like this, so this is a generalized scalar structure. So we'll say that this with a smooth function, generalized scalar structure with a smooth function is gradient steady generalized scalar Ricci soliton. GKRS stands for generalized scalar Ricci soliton. If it solves the following system of equations, usual Ricci curvature minus 1/4 H contracted with H. There is only one contraction, which makes it positive definite symmetric tensor. Hessian F equals 0, and d star of, should I rewrite it like this? E to the negative FH equals 0. So this is a system of equation which we're trying to solve. And this is not the random system. We have seen it appearing many times already. These are, in fact, stationary points of the Perelman functional. Stationary points of Perelman's functional. And for instance, the consequence of this fact that these appear as stationary points of generalized scalar Ricci flow on compact backgrounds or on complete backgrounds with appropriate decay, if you allow also flow by diffeomorphism. So we are interested in this, and the one example which I can give right away is at the standard Hopf surface above. Standard Hopf. So the one we considered MGIJ is a soliton. So when I say soliton, I mean gradient steady generalized scalar Ricci soliton. With the function f just being 0 or constant. So in some sense, it's not an interesting example. It's in a sense trivial because f is 0. But I mean, it's also interesting in some case, some circumstances, because this in particular happens to be Bismuth-Ricci flat. This is a setup which Josh and Mario discussed, last 2 times. So these are equations which we're interested in, and maybe let me make a little proposition about like existence and non-existence of those. Suppose your torsion form H is actually exact. So we know it's closed. Assume it represents a zero class in homology. It's exact. And yeah, and MGIJ is a soliton. Is a soliton. Then we immediately maybe add also compact. Is a compact soliton. Then actually it has to be that MGI is Calabi-Yau. Is Calabi-Yau Kähler. And F is constant. And the same work is true for J. So how does it work? Well, we have this equation, which I deliberately wrote in this form. Then I can integrate over my manifold, because of my manifold is compact, contraction between B and D star of e to the negative FH. With respect to the volume form. So it's zero because this term is zero. Now integrating by parts, I can rewrite it as integral over M dB squared. So this is H integrated across e to the negative F dV, which implies that H has to be identically zero. So both I and J are Kähler-Ricci solitons. Kähler-Ricci solitons. So they are both Kähler and H is identically zero. So this term disappears from here. And if you remove this term, what is left is exactly Ricci soliton equation. And any Kähler-Ricci soliton, any compact Kähler-Ricci soliton, any compact Kähler-Ricci soliton is Calabi-Yau. So H cannot be exact. It has to be represented on zero class in homology if we want something non-trivial, something which is not Calabi-Yau and where F is allowed to be non-zero. And actually, there is a natural setting where H is necessarily exact, and I'll make this remark. If MGIJ as the symplectic form F plus globally defined, then H is exact. It's pure consequence of this relations of the tensors on the generalized scalar background. You can actually show that H. So I'll try to write down. I hope I didn't mess up with signs. Okay, anyway, up to sign, it's 0, 2 minus 2, 0. With respect to I. So, which means that if you have a symplectic type generalized scalar structure, then you have only trivial solitons. So you don't have any interesting solitons. And for these reasons, we would like to consider from now on, and we're really sort of forced to consider examples which are not symplectic with respect to F plus. So F plus is not globally defined. And likewise, analogously, F minus cannot be globally defined. So the same remark holds with F plus instead of F minus instead of F plus. So we have to consider non-symplectic setting. Non-symplectic setting. So we have to allow for it. And are there any questions to this point? So what we did, we decided to consider the next best thing. So next best thing which you can assume. Next best thing. is logged undegenerate. Which means, as we discussed, that F plus and F minus and sigma are defined on open dense sets. On a common open dense set. So that will be our assumption to the rest of the talk. So before I actually exploit this assumption, let me also formulate a general proposition from our paper with Jeff. So it turns out that similarly to the Keller setting, there is a special vector field, and actually two vector fields associated to any generalized Keller-Ricci soliton. So the following are equivalent. So again, I always assume from now on that M is compact, even though it's actually not relevant here, but in general, I assume. This is gradient steady soliton, gradient steady generalized Keller-Ricci soliton, and the fact that the vector field xi, which I define as 1/2 I. So I'll explain in a second what this notation means. Minus grad f is Keeling and I holomorphic. And Bismuth 1,1 part equals negative Lie derivative of I x I omega I. So I have to explain here one thing, that we need to explain what is theta I sharp. So theta I is the Lie form we're characterized by the identity that d omega I to the power n minus 1 equals theta I wedge omega I to the power n minus 1. This is the definition. Theta I sharp is the corresponding vector field which you obtain by raising by one index. Okay. So what we see here, that necessarily any soliton has a very special vector field, which is Keeling and I holomorphic. And actually one part of the Bismuth Ricci form is related to the derivative of I x I. And maybe also write that the same can be written for J complex structure. So for xj, which is defined analogously with j instead of I. So this whole system of equations can be rewritten in these terms, which is arguably a little bit more geometric. So such vector fields, so vector fields in this form, they actually are kind of special from the point of view of logged undegenerate generalized Keller structures. So I'll make a claim. So this claim doesn't assume soliton equations. This claim actually is true in general. So on any generalized Keller manifold, and xi defined by this formula. Again, f can be any function here, and xj defined by an analogous formula. So you just take this vector field. Since it's any generalized Keller structures, they don't have to be Keeling, they don't have to be holomorphic, they're just vector fields. But these vector fields nevertheless satisfy some structure, and specifically, it is true that xi plus xj is Hamiltonian with respect to symplectic structure f plus, and the difference of these two vector fields is symplectic with respect to Hamiltonian with respect to F minus.
Sorry, is this claim holds for any function or
Yeah,
for some
any function.
specific?
Yeah, any function. Yeah, any function.
Okay.
Yeah, and Hamiltonians, maybe I call this Hamiltonian psi plus here and psi minus here. Again, maybe, okay, let me write it down. So F plus of xi plus xj dot equals negative d psi plus. F minus of I minus xj dot equals negative d psi minus. And specifically, you can write down what these psi are. So psi plus or minus is 1/2 log determinant I plus j plus or minus minus f. So psi plus or minus are not defined everywhere. They're defined only where I plus or I minus j is invertible, and this is the same locus where f plus or f minus is defined. So the domain of psi is the same as the domain of f. So it's an immediate calculation. It uses an amazing identity which Vesti and Jeff found in their paper, which I don't have a good understanding for why this identity is true. I'll just write it down. So this identity is essentially what is used here. So the identity is between the Lie forms of I and J, and it tells you that, I mean, this identity is essentially the proof. So d of log determinant of I plus or minus j. Again, this identity is very special. It's a consequence of by Hamiltonian definition of generalized scalar structure, but it's still amazing that you have this type of formula, because you see the right hand side. In general, it's not globally defined, right? Because this thing might vanish, and log determinant will be then singular, and its differential will be singular as well. Then if you multiply again by the same operator, somehow you get one form which is smooth on the entire manifold. So left hand side is globally defined with this identity, and the right hand side defined only on the open dense set. And it has an interesting consequence, this fact. So I can actually rewrite this defining identity of psi plus and psi minus as follows. I can write it as e psi plus or minus f plus or minus to the power n over n factorial equals e to the negative f, and this is the volume form. So this is equivalent. The definition of psi, the formula for psi written here is equivalent to this one. But let's look for a second at this identity. So what this identity shows us that this form, which is a priori is not globally defined, right? Because f is not globally defined and psi is not globally defined. They have singularities along the locus where I plus j becomes degenerate. Nevertheless, this product extends to a globally defined smooth volume form like this. So it's a remarkable fact which will be important later.
Is the Hamiltonian flow of these functions related to the generalized Ricci flow?
That is a good question. The answer is yes. The Hamiltonian flow, well, not Hamiltonian flow. How should I put it? Well, you know, the answer is I don't know. So the difference of psi plus and psi minus is something which Jeff and Vesti call capital phi in their paper. So the difference is the logarithm of the ratio of determinants I plus j and I minus j, and that is related to generalized Ricci flow. Actually, if you take sigma Hamiltonian vector field of this difference, then this is what generalized Ricci flow does. But yeah, it's not related to f plus and f minus specifically. So maybe I'll write this here. So generalized scalar Ricci flow is the I put in quotes the Hamiltonian construction. Hamiltonian flow construction of the function psi plus minus psi minus. So the difference of these two functions can be put inside this machine of Hamiltonian flow construction, and the deformation is what generalized scalar Ricci flow does. The reason why I put quotes here is because this function is actually not smooth on the entire manifold. If you remember our definition, we wanted our function phi to be a smooth function on your manifold, while this is not. And even though it's not, its Hamiltonian flow construction is well defined. So again, it's...
Yuri, I have a question. Just forgetting some details. But so this relation that E psi plus E f plus n is globally defined, is that determines eventually xi and xj completely, or you're not sure?
No, I don't think it determines xi and xj. Yeah, that's actually a good question. That's something I've been thinking recently. I don't think it's alone determines. So you have some information about xi and xj from here. That is true, because basically you know the behavior of the corresponding Hamiltonian potential along these two divisors. But I don't think it completely tells you what the vector field is. I have suspicion that maybe it does, and it will be statements similar to the statement that holomorphic symplectic manifolds do not have continuous symmetries. So I expect that it's something might be related to this, and actually they might be uniquely defined. But yeah, I don't have such a statement. Okay. Are there more questions? So now let me formulate.
Sorry, maybe can I just make a comment? I mean, I think even this thing you write, the generalized scalar Ricci flow is the Hamiltonian flow of psi plus minus psi minus. I mean, I guess, yeah, I mean, we definitely proved that in the non-degenerate case, and it's probably almost certainly true in the case you described, but I'm not actually sure we sort of rigorously proved that anywhere. Well, I mean, I think there's still sort of something to show, right?
No, I don't think so,
no?
because this is defined on the open dense set. And on the open dense set, you have this formula for the Bismuth-Ricci in terms of capital phi. So this is actually what is called capital phi.
And like we know for sure that that the associated vector field is actually global.
Yes. Well, okay.
Does it actually?
Well, yes, because we know that
because it somehow, I guess, has to be just because it's somehow inducing.
I think it's global.
Actually, the vector field might not be global. That's the thing, but the variation of complex structure can be extended globally.
Well, yeah, that's clear. Yeah.
But even in the vector field, I think it will be global actually.
No, it might be something like singular and holomorphic. It might be holomorphic with respect to J and singular along this loci. I think vector field is a holomorphic singular vector field plus a smooth vector field.
Doesn't the Poisson structure also vanish exactly? The Poisson structure vanishes exactly where the determinant would vanish.
Yeah, precisely.
That's right. Yes.
Which would cancel out.
Yeah, I think so. Yeah, I believe Francis is right.
Okay,
but we have to check it again. It's.
Yeah, maybe you're right. Yeah, so yeah, Jeff, yeah, I guess you're right that you need to check something if you want to show that your vector field extends smoothly.
Yeah, but maybe probably it does kind of follow from the identity in the middle of the page. Just simply knowing that I plus j d log determinant I plus j and then also minus are both smooth, probably.
Yeah, you probably are.
Probably that's. But yeah, anyways.
Okay, so yeah, that's that special fact about such vector fields. And yeah, recall we have these vector fields because they characterize, they participate in this characterization of the solitons being Killing and I holomorphic or J holomorphic and being related to the Bismuth region. So now I will kind of refine our knowledge of what these vector fields are and what they satisfy. So I will formulate a proposition. I will probably not prove it. And yet there is actually a question about this proposition, which I don't know how to answer. So maybe anyone can be able to tell me. So let G I J be gradient steady generalized scalar Ricci soliton. So then what we can conclude. So first, that Lie derivative of Ixi sigma or Lie derivative of Jxj sigma. So these both vanish. And as a consequence of that, we can conclude that derivative of sigma with respect to xi and derivative of sigma with respect to xj also vanish. So they preserve Poisson tensor. So I make a comment about this. So this is actually a consequence of the fact that sigma doesn't change along generalized scalar Ricci flow. And generalized scalar Ricci flow in either I fixed gauge or J fixed gauge is essentially a flow by this vector field on a soliton. And for this reason, since it's in general known that sigma is preserved along the flow, we have these identities. And we have this consequence essentially because sigma is a real part of an I holomorphic Poisson structure and or J holomorphic Poisson structure. And these vectors are respectively I or J holomorphic. So this is true in general, actually. I don't have to assume anything besides the soliton condition. I don't have to assume log non-degenerate. If on top of that, you assume that your structure is log symplectic, so meaning that F plus or F minus is defined on an open dense set, then you can actually prove that Xi and Xj are both I and J holomorphic. So remember, so far, Xi was I holomorphic and Xj was J holomorphic. It turns out that if your structure is log symplectic, they both will be holomorphic with respect to both structures. And here I have a question which I don't know how to answer, and I suspect it is true, but I don't have an argument. So is it true in general? Is it true in general? So without this log symplectic assumption. So yeah, that's unclear. And again, as a consequence of this, you can sort of easily check that they must commute. These are commuting vector fields.
Sorry, can you clarify? So are you saying that Xi is I holomorphic or that Xi is both I and J holomorphic? And...
Yes, they both are I and J holomorphic.
Okay, thanks.
Because we already knew that Xi is I holomorphic and Xj is J holomorphic. Now they are both simultaneously I and J holomorphic. So they essentially preserve the entire structure. They preserve metric, they preserve I, and they preserve J. So they preserve everything what's possible. And final observation. So if compact, again, so far these are local arguments. So the proof doesn't even use compactness. So if your manifold is compact, besides that, what you can check that F plus or minus of Xi, Xj is 0. So they are orthogonal to each other with respect to F plus or F minus. And again, you can rewrite it a little bit. I'm not sure if it's really more helpful or not. You can rewrite the above. Again, whenever sigma is invertible, you can write that Ixi and Xj are paired to 0, and Xi and Jxj also paired to 0. So this is essentially equivalent to the previous one. So yeah, the question which I'm asking here is whether we can remove log symplectic in this place, and I don't know. So what it does, this proposition, it shows you that on a log non-degenerate gradient steady soliton, you have two vector fields which are very special, which both preserve the entire structure. So there's xi and xj, they preserve g, I, and j all together. So they generate a subgroup in the isometry group, and because they commute, they actually generate a torus inside of your isometry group, which preserves both holomorphic structures. And this is the key to the following proposition, which I will call as volume characterization of solitons. Volume of solitons. You should think of it morally as some version of Monge-Ampere equation for solitons. Monge-Ampere equation is a characterization of Kähler Ricci solitons, or in general, all canonical metrics in Kähler geometry are defined through some version of Monge-Ampere equation. So something similar happens here for gradient steady solitons. So we assume the following. So MGIJ is a compact log non-degenerate generalized scalar manifold with vector fields xi and xj such that, so these are just arbitrary vector fields satisfying certain properties, and they will be, in the end of the day, the xi and xj corresponding to the soliton. So with two vector fields such that they first xi, xj preserve matrix, so they're killing, and they preserve I, they preserve j, and they commute. So second assumption is that xi plus xj is f plus Hamiltonian. And likewise, f minus Hamiltonian vector field would be xi minus xj. So third assumption is that this normalized volume form e to the psi f to the n over n factorial. So again, plus or minus. So this is a vector volume form which is defined on an open dense set, and the assumption is that it extends to a smooth volume form. And finally, so yeah, Hamiltonian with potentials psi plus or minus. And the key equation is the next one, that this two volume forms which are obtained after extending it across the entire manifold, they are equal to each other. E to the psi plus f plus over n factorial equals e to the psi minus f minus over n factorial. So this is the key equation here. So if this happens, if you have these two vector fields and they satisfy this list of properties, then your manifold is generalized scalar Ricci soliton, again gradient steady, with potentials. I need to specify my function little f. So this potential is the log of the ratio of two volume forms of the Riemannian volume form and this volume form, either this or this. E to the psi plus f plus over n factorial minus psi plus. So it's specific. I deliberately wrote, sorry, yeah, I meant to remove this function. Or I can put e to the psi plus here if you would like to.
So Yuri, I have a naive question. So
Yeah.
it's just forgetting number 4. So I start with a generalized scalar without non-degenerate and a torus 2T action.
Yeah.
A two-dimensional torus action. And can one always satisfy 3 for a unique choices of elements in the Lie algebra?
Yes, I don't think so. Yeah, I don't have no. Why?
I can see that there are at most well, if you can satisfy, then I think this will determine xi in J already, because we cannot take combinations and this still to be true, or even if you add a constant to the potential, also you disturb everything. So it looks to me that this 3 is quite significant.
It is significant, yeah, but you can take convex combination if you have 2 choices, right? And still satisfy this convex combinations of potentials.
But if C minus F plus N will be not globally defined. So what do you mean by convex?
No, yeah, what I'm saying, I don't see exactly uniqueness of the vector fields yet. Yeah, maybe I'm missing something simple. But in principle, I don't see a problem, any issue with the fact that there is another pair of vector fields, yi and yj, satisfying the same assumption.
But if I take a linear combination of C plus and C minus and try to satisfy the condition with F plus.
No, the linear combination of C plus and C minus, yeah, it will not satisfy anything. But maybe there is
only C plus will do. So it determines the first vector field and similar for F minus. So you get that.
No, I don't understand why they might. So we will have this ipsi plus f to the n over n factorial, which is globally defined. Maybe there is some other function. I don't know.
Well, you have the torus action fixed. Everything is fixed. So in general, these things are determined by.
I mean, if your torus is 2-dimensional, then yes, but you might have a lot.
That's my question. It's 2-dimensional.
Oh, okay. Your torus is 2-dimensional. Yes, then you're right. Yes.
Okay.
Sorry,
so
I missed this point. Yes, if you have a small torus, if you know that you have a small torus of automorphism, then you're correct. Yeah, my concern is rather in the situation where you have a large torus and you don't really know which vector fields to pick. So you have some choice.
Okay.
Thanks for the question. So yeah, I will not go to the proof in details, and maybe again I'll mention this one remarkable formula from Jeff's and Vesta's paper. So basically, as I mentioned, this capital phi is the difference. Well, I think if their signs should be right, it should be psi minus psi plus. So for this function, you can use it to calculate Bismuth-Ricci. So the Bismuth-Ricci will be 1/2 dj d of phi. So using this formula for Bismuth-Ricci, essentially all you need to check is that condition from the proposition which I mentioned. Maybe I'll scroll up for a second. So we had this characterization of gradient Kähler-Ricci solitons, and we already have a vector field which is Killing and holomorphic. So really everything we need to check is this identity. So some formula for the curvature. And this formula for the curvature exactly follows from that identity which I mentioned and the assumptions of the proposition. So I'm going to go further in details. Yeah, I don't have much time. So Jeff, what should be? So yeah, I spent a lot of time that I meant. So Jeff, what should be our plans? Do we have speaker for the next time? Hello?
Sorry, hello?
We hear you, but Jeff disappeared.
I'm sorry, I had to walk away for 1 second. What was the question?
Yeah, so I have a little bit of material to talk about. I was wondering, does it make sense for me to finish now, or we could like proceed now to the next week?
We could actually put it off for next week because actually the schedule kind of got messed up and it was supposed to maybe be Francis, but he had already told me he couldn't. And then I tried to maybe get one of Marco's students to do it. So yeah, anyways, bottom line is, yeah, maybe it's better to stop and go ahead.
Yeah, maybe I'll just recap what we did, tell what I will do next time. There is not much left, but yeah, we can discuss something else along these lines.
Yeah,
so
no,
we
sure.
got this characterization of solitons through the volume equation. So what we now want to understand what happens with this volume equation inside generalized scalar class. So if I take a generalized scalar class and it have some structure, I have these two volume forms which may be different. So what happens with these two volume forms if I take the variations along the flow construction sitting inside generalized scalar class? And at the end of the day, I would like to put up a functional whose critical points will be exactly structures satisfying these equations. So functional on the generalized scalar class. And yeah, that's what I want to discuss next time. There is not much to present, but there is a little application in the context of Hopf surfaces. So we might discuss that as well, about generalized scalar structures on Hopf surfaces. So yeah, that's a plan for next time.
Well, okay, yeah, that's great. So yeah, thanks, Yuri.
Yeah, thank you.
Thanks.
Thank
So
you.
what do you know in this log non-degenerate case about the vector fields xi and xj? Are they generically non-zero or something? Or it's not clear?
Well, they might be zero. There are complete examples where there is zero. There are no interest. I mean, there are, of course, Calabi-Yau examples, and there are general and generalized scalar examples where they're complete. On the Hopf surface, which I mentioned before, they are non-zero. They are an actual true vector field, holomorphic vector fields on the Hopf surface. Well, what I know is that they vanish at these two loci where Poisson tensor vanishes. I don't think I know much besides that.
I was wondering about what does this tell you about the geometric structure of the manifold? Because if these are non-zero, then you have this foliation.
Yeah, you have foliation. Yeah, that's actually the key idea in what we're now trying to do with Jeff and Basti. So what you can do, you can take this to vector fields, and at least in 4 dimensions, for instance, you can take this to vector fields, and you can consider the complementary direction, the transversal geometry to vector fields. And in transverse geometry, you happen to have the same type of structure as on toric Kähler manifolds. And the equation which you are solving is the same equation for the toric Kähler Ricci solitons, which is a real Monge-Ampere equation.
Nice.
But also another significance is that if you wedge these two vector fields in 4 dimensions, you get a real constant times the Poisson tensor.
Yes.
So which to me is always very mysterious, but that's one significance.
Mm-hmm.
Maybe this we combined with Yuri's condition number 3 will determine them uniquely in a general situation.
Yeah, maybe. Yeah, I feel it has to be something because it's like a little tiny step away from holomorphic symplectic. We're almost holomorphic symplectic apart from like presence of these two divisors. And these vector fields are essentially there, I think, because there are these two divisors. In general, there shouldn't be other symmetries apart from this vector field. Well, it's not quite that, but it's a little bit more subtle. So that's why I don't know exactly how to answer this question.
You said that the wedge product so the Poisson structure is essentially xi wedge xj?
In complex dimension 2, yes. And again, under the compactness condition. If you don't have compactness condition, I don't think it's true. We have non-compact example where xi is proportional to xj and where Poisson tensor is non-zero. Okay, under certain assumption, it is true. Yeah, perhaps what is true that the xi wedge xj is a constant multiple of Poisson tensor. Perhaps
yes, that's right. That's true. And you have two cases. This constant is zero or non-zero, and it's a real constant, which is quite remarkable.
It's a real constant.
Well, okay, so yeah, should we close it down? And then, so you'll go again next week, Yuri?
Yeah, I'll probably take less time. So I'll try
That's
to do
perfect.
that,
it's like Thanksgiving week too.
in an hour.
It's
Maybe
perfect.
under that.
Yeah.
Sounds good.
And then, so wait, hold on 1 second. But then I forgot what exactly I said to people, but like, or maybe can you go after that, Francis? It's okay for you to go? Okay. So then probably I can just push what currently exists 1 week down the road, I think. And then I think it's all okay.
So I would speak on the week of the 30th. I would speak on the 30th. Is that right?
Yeah. Is it okay?
Let me just check. Right. So it was next week. That was a bad date. Yeah, the 30th is perfect.
Okay, great. Okay. So yeah, thanks guys.
Thank you.
See you next
Thank
week.
you. Bye.